Okay, so let's go through this nice example problem. Let's go ahead and read the problem. I compress the spring a distance of 0.4 meters. I then release the spring, launching the mass 5.3 meters up the slope. What is the spring constant? Assume there is no friction. Okay, so this is an interesting problem. It's a lot like a pinball launcher, right? To launch a pinball in a pinball machine, you compress a spring and then you let that spring go, and it launches the pinball up into the machine, right? So the same type of thing is happening here. We have some object, this mass, right here, which is initially at the equilibrium position, right? That spring is neither stretched nor compressed, and then we're going to compress that spring 0.4 meters. Okay, so that means we're going to push on the mass in this direction until the mass gets to here or so. And in doing so, we've kind of, compressed that spring. The spring is all compressed, and we've stored energy in that spring. Okay, so this distance is equal to 0.4 meters. So that's one of the knowns they gave us in the problem. I then release the spring, launching the mass 5.3 meters up the slope, and we want to know the spring constant. Okay, so how do we solve this problem? How do we solve for unknown? What concepts can we use when solving this problem? Well, we have a few clues from the problem. First is that there's no friction. No friction means that if the only forces involved here, which are doing work, are the elastic force, the force of the spring on the mass, and the force of gravity. Those are both conservative forces, so we know that we should be able to use conservation of energy to solve this problem. Right? So if you have things like gravity and elastic forces but no friction, you can typically use energy conservation to solve that problem. So that's a good clue. We also know that anytime we have a spring, because the force of the spring, what we call the elastic force, depends on displacement, depends how far we've compressed the spring, it means that as that spring uncompresses, the force is going to be changing based on distance. Right? And so that makes problems somewhat tricky to solve if we try to use like force ideas to solve this problem. But because of the magic of work and energy, we've taken that into account already in the integral for work. When defining elastic potential energy, we took into account the fact that this force is changing. Right? So anytime you have a spring, energy and work type solutions are typically the way you want to go. Okay, and so let's try to use conservation of energy to solve this problem. And so our goal is to figure out at time 1, what is the total energy of our system, and at some later time, what is the total energy of our system. And conservation of energy tells us that that energy has to be the same, right? The energy has to be a constant. The total energy of the system has to be constant. And so let's go ahead and just think about, I'll call this time 1, when we've just compressed the spring, but the velocity of the mass is 0. So we're just about to release that mass. And let's call time 2 when the box is at its highest point up the slope, right? So at that moment, the velocity is equal to 0. Okay, same thing at time 1, the velocity is equal to 0. Okay, and so with time 1 and time 2, we can think about what energy is involved in the system. Right? At time 1, well, my kinetic energy at time 1 has to be 0, right? Because my velocity at time 1 is equal to 0. My potential energy at time 1 is non-zero, right? Because I have stored elastic potential energy, right? In compressing that spring, I've done work, I've stored energy in the system. That mass now has a potential to turn that stored potential energy into kinetic energy. So at time 1, I have elastic potential energy. We have an equation for that. 1/2 times the spring constant, lowercase k, times our displacement. Right, how far away from equilibrium are we in that moment? Okay, so we know we have only one type of potential energy at time 1 because we've defined the ground to be y equals 0. So there's no gravitational potential energy at time 1. What about at time 2? Well, at time 2, we also have no kinetic energy, right? Because once again, the velocity at time 2 is equal to 0. But at time 2, the mass has risen up some distance in the y direction, right? So we do have gravitational potential energy at time 2. So I can use our equation for gravitational potential energy, where I can say this height is the distance in the y direction away from the origin that this mass has risen. Okay, and so we have gravitational potential energy. That mass has risen up into the air, and it's now we could let go of it, and it'll slide down, and that gravitational potential energy will convert back into kinetic energy, for example. And so, okay, this is very helpful, but the problem is asking about. The problem told us one extra piece of information, which is the mass went 5.3 meters up the slope. All right, so that's telling us that this distance is 5.3 meters. Okay, and so we need to relate that given piece of information to this y2 so that we can plug into this formula. All right, so I can see that I have that sine of 45 degrees is equal to opposite, which is y2, over hypotenuse, which is 5.3 meters. So I could use that to solve for y2. Okay, so let's just plug in to our potential energy formula here. This is equal to 1.5 kilograms times g, which is 9.81 meters per second squared, times y2, which is, by this equation that we just derived, is 5.3 meters times sine of 45 degrees. So plugging that all in, I can find that the gravitational potential energy at time 2 is equal to 55.15 joules. Okay? And I don't know what my elastic potential energy to start with is because I don't know my spring constant. That's my unknown. But at this point, we can now go ahead and use energy conservation to solve for our unknown. Right? Energy conservation is a very simple formula. E1 is equal to E2. Right? Whatever my total energy at time 1 is equal to my total energy at time 2. In general, my total energy at time 1 is just going to be the sum of my potential energy plus my kinetic energy at time 1, where the total energy at time 2 is just the sum of my potential energy at time 2 plus my kinetic energy at time 2. And we know that kinetic energy at time 1 and at time 2 are equal to 0, right, because the object is at rest at those two times. So this means that U1 is equal to U2, and we know what U2 is. It's equal to 55.15 joules. Okay, so this will enable us to solve, right, because we know what U1 is also. It's equal to 1/2 k times delta x squared. Right, so let's plug that in. This means 1/2 k times delta x squared is equal to U2, and I can solve for k. K is equal to 2 times U2 over delta x squared. And I have numbers for all of these things. This is 2 times, again, 55.15 joules divided by delta x squared, which is 0.4 meters squared. And so, sorry, I'm running out of room here. Plugging this in, we solve for the spring constant and find it to be 689 newtons per meter. Okay, so that is our final answer. And so this is a really nice example of using energy conservation to solve for an unknown. Let me know if you have any questions on that.